Hi everyone, Professor Mankowski here. In this video, we're going to be doing section 3-2, which is measures of variation. And measures of variation in the introductory statistics class is usually where the formulas start to get pretty complex. So we're going to ease into this discussion with a conceptual understanding of what variance is all about, and then we'll work our way into the formulas. So what we're going to do is we're going to start with two different data sets. And if I were to give you $100 to bet on which number comes next, you just have to pick one data set to bet on, which data set would you pick? Now, everybody's probably going to pick the first data set. How come? I mean, the data set on top, because it's probably going to be 1 as the next number. It's very predictable. The data set that's on the bottom is a lot harder to predict. So if we put the $100, we take a shot in the dark on the data set on the bottom, it's going to be really hard for us to get that next number right. So what we're starting to talk about is the data set on the top has a much less variation. Literally, the numbers from one value to the next, they vary a lot less. So what we're thinking of is if we consider a data set that has a low variance, it probably means it's going to be a very stable data set. We would say it's predictable, and it's probably risk-free. Like if we're going to base a forecast or a prediction on some kind of historical information, and that historical information is a data set that looks like the one up there on the top, it's probably going to be a lot easier for us to get the forecast correct, which means it's less risky. Now, what about the data set on the bottom? That's a higher variance. So what kind of words do we associate a high variance with? Instead of stable, unstable. Surely not predictable, but unpredictable. And instead of risk-free, probably a lot more risky to use that data set. So what happens is, in the statistics, when we are doing forecasting, when we are doing predictions, we have to base our prediction on some kind of a historical data set. And how variable the information is has a lot to do with how much error we're going to have to involve in our forecast. So it becomes really important to be able to have some way of gauging how much variability is in the data set, because that has a lot of implications for how much error we have to include in our calculations. So how do we do this? How do you quantify variability? And got 3 ways to do it: range, variance, and standard deviation. So what we're going to do is we're going to ease into an example of how the range works. And we're going to find out the range is a pretty basic way of estimating variability, but it's got a lot of shortcomings. And pretty soon we're going to see that it has too many shortcomings, and we're going to need something much more sophisticated. And that something much more sophisticated is going to turn out to be the variance. Variance and standard deviation are joined at the hip to each other. We'll see why you would use a variance instead of standard deviation coming up in the videos. So what we've got on the bottom, 2 different data sets. And these are brands of paint, brand A on the top, brand B on the bottom. And disregard the part that says in months in parentheses. What we're going to do with the data sets is they represent for us the hours of time it took for a coat of paint to dry using that paint. So the data set on the top, 10, 20, 30, 40, 50, 60, different drying times. Like far left, somebody took a coat of paint with brand A, and it took 10 hours for that paint to dry. Next in the sample was 20. So somebody painted a room or something like that and took 20 hours for the paint to dry. And then 30 hours. If we look down on the bottom, in one instance, it took 25 hours for the paint to dry, brand B. Another instance, 30 hours. And then twice through, 35 hours. So if we're a professional painter and we go into Home Depot and they say to us, you want to buy some paint? Well, we have sample drying times from brand A and brand B. Pick which one you would like based on the sample drying times. Which one would they probably use, brand A or brand B? And the answer is they probably use brand B because the drying time is much more predictable. There's a range of that looks like it's much more narrow than for part A. Like brand B will dry anywhere from 25 to 45 hours. Brand A takes anywhere from 10 to 60 hours. That's a really big window. So when we think about how we can start to quantify what we're seeing, the range will do the most basic job for that, of quantifying the dispersion, meaning how spread out a data set is. It looks like data set A is much more spread out than data set B. So let's see how that works. The range is going to help us by calculating the maximum minus the minimum number in each data set. So if we look at the range of A, the maximum dry time was 60 hours, the minimum dry time was 10 hours. So that makes the range 50 hours. Range for B is going to be 20 hours. So what it's kind of telling us is that the data set A is taking up physically much more room on the number line than data set B. There's in data set A 50 hours in between the minimum dry time and the maximum dry time, and B, that's only 20 hours. So B would have to be physically a much tighter window. That lets us know that A has to be more spread out, more widely dispersed than data set B. So we like the range because it's quick and it's fast. Like it just took us a couple minutes to subtract and get the answer. But there is this really big problem with the range, and we're going to take a look at that in the next screenshot. Now let's work with data set A for a while. We're going to go away from data set B because we want to keep things simple. And imagine that we had a really big structural structural change in the data set for brand A. All of our values shifted, and we got all these new dry time amounts. Those are the X's that we see. And we're going to compare the original dry times right below. So we're keeping both the new and the old. So look at where all the X's are. Did we just have a huge structural change in that data set? And the answer is absolutely. All the drying times, they're crushed up on the left side of the data set now. So it has really profound impact, right? Pretty big. Now, big question is, did we detect that change with the range? And the answer is no, we did not. The range is still holding at 50. And that's really bad because it means data set changed massively. And we need the range to be able to tell us information about dispersion of the data set, how spread out the data set is. And this dispersion changed. All the numbers are crunched up on the left, and the range is not doing anything to help us. Like it's totally blind to what just happened. And that puts us in a really bad spot because what it means is the range can see the highest number, rather the lowest number and the highest number, but it cannot see anything in between. So it's totally blind to what's happening in the inside of the data set. So the range is kind of nice and fast, but it's not very usable in the end. And because of that, we have a need for something that's going to be much more sensitive. We need some kind of a calculation that's going to take into effect the position of every single number in the data set and not neglect anything. So what we could say is the range is the least sensitive measure of dispersion. Now, how do we overcome all this? Like we'd say, well, we have to do better, obviously, so what's better? And the answer is going to be variance. What variance is going to do is it's going to consider the position of every single number in the data set. It's going to take everything into account. And what it's going to try to do is measure the distance, measure the average distance between each observation and the mean. So if it's going to do that, if it's going to measure the distance between each number and the mean, if the variance goes very low, it means each number must be very close to the mean of the data set. And how I like to remember that is, I think of that picture on the left, all those people crunched up in the elevator. Well, those are like your values that are all very closely crunched up around the mean of the data set because they're not far from the mean. The average distance between each number and the average is next to nothing, so all the values are kind of crunched up around it. If you have a really high variance, it means the data set is very far spread out. That's where you get the picture on the right, like all those people stretched with their arms out really far and wide. Think of those as they're all observations really far away from the mean because each number on average is a much greater distance away from the mean now. Okay, so how do you calculate your variance then? And I'm gonna move this out of the way. Come back to this later on. Okay, so we know that the variance is trying to measure the average distance between each observation and the mean. So what I'm going to do is I'm going to start by just listing all my X values right there down the side of the page. And then what I'm going to do is I'm going to put in my X bar. my sample average. And I'm just going to list all the averages right down next to my data values. And that's going to be to help me subtract each value from the mean much more easily. So in the next column, I'm going to say what I'm about to do. I'm going to take each x value, subtract it from the average, and right in there, I'm going to pencil in all the differences. Now, it looks like I'm set up pretty well. All I have to do is I have to go ahead and get the average of all those distances. Looks great. The only problem is we can't do it. The reason why is because all the negatives are going to cancel out with all the positives, and we're going to get left with absolutely nothing. So basically, this is useless. So what do we do to go and try to improve things? And the answer is you have to do something to keep the negatives from canceling out. So what would do that? Like, what takes a negative and turns it into a positive? The answer is we could go and we could take each of those numbers and we could square them. That's exactly what we're going to do. So in the next column, we go ahead and we write in all of our squared values. And what we have to do now is we have to add up this whole column. And we get the sum of that. And now what we're going to do is we're going to bring that up a little higher on the paper. We're going to write in 1,750. So if we're going to take the average of all those numbers, we would take 1,750, and this is the freaky part. We're going to divide it by 1 less than the total number of observations we have. We'll talk about that later on, why we're doing 1 less than the total number of observations. And we'll just take a minute here. We'll kind of tap the brakes, and let's just review what we did. So I'm going to use my pointer arrow here. And the first thing that we had to do was we took each data value, each x value, and we subtracted each x value from the average. And that's what we ended up with right here. Here's each x value. We subtracted it from the average. And in our formula, right over here, we see it taking each x right there. It's telling us to subtract from x bar. And then what do we do after that? Well, we had all of these distances, right? All these distances from our difference, and we found out we had to square them up. So right over here, we did our square functions. Now in my formula, over here on the far right side, I've got a square right there. That's taking care of the squaring operation. Now at the end, once I had all these distances squared right here, I had to add all of those up. My sum was 1,750. So in my formula, I have my summation sign. I'm saying go and add that whole column up. Now I had to divide by, I took 6 and I subtracted 1. So 6 in symbols would be my n for the total number of observations. And then I subtracted 1 from it. When I do all that out, I do 1750 divided by 6 minus 1. I'm going to end up with 350. Now, 350 is going to be my variance. And I have a short term for that. I mean, an abbreviation for variance. I'm going to call that s squared. And s squared you have to memorize because we're going to see s squared almost everywhere between now and the rest of the course. You have to know that s squared means variance. Okay, so now we know that the average square distance between each value and the mean was 350. Let's hop over into the next slide here. And here's our next slide. Okay, so originally, remember, when we set out, all we wanted to do was calculate the average distance between each average and the mean. I mean, each observation and the mean. Keep it nice and simple. And now we have the average squared distance between each value and the mean, which is not what we want. So how do you do that? Like, how do you get rid of the average square distance? Because we don't walk around talking in terms of the average square of anything, really. So we have to think of what's going to reverse a squaring function, and the answer to that would be a square root. But think of maybe like if you have a part-time job, you make $10 an hour. Somebody says to you, how much do you make? We won't say $100 squared an hour. Like if you drove 10 minutes to get to your job, you wouldn't tell somebody I drove 100 squared minutes. It wouldn't make any sense. That's why we're taking the square root of the variance, because we want to get into units that are relatable. So we know a square root should undo the squaring. This is going to bring us to the standard deviation. What the standard deviation is going to do is the standard deviation is going to abbreviate as S. And the standard deviation is literally equal to the square root of the variance. So in our formula, we see that on the far right there, all we're doing is taking the whole variance formula and we're putting it under a square root sign. And for us, if we take that square root, that's going to come out to be 18.7. So that means our standard deviation is 18.7. And this should be our note hand here. Standard deviation is abbreviated not as s squared, but as s. So we need to change that. Okay, let's get back to where we were. Okay, so s is equal to 18.7. Now, the big question for us is, what did we really just calculate? What does 18.7 really just mean? We know that's the average distance between each value and the mean, but in practical context, what's that all about? So here's the answer to that. Picture that you pick up a can of paint. You're looking at the label, just like we have here in the viewfinder there. And we're thinking about the label of this thing. It's got all these things written on it, right? Like all these stupid warnings, like don't drink the paint for breakfast, don't swallow the paint or anything like that. Now, they'll probably have product specifications on it too. And among other things, they're going to tell you the average dry time of the paint. So if we know that the average dry time was, I have to move this out of the window here. If we know that the average dry time was 35 hours and we go to paint a room with this paint, do we expect that room to dry in exactly 35 hours on the nose? And we'd say, well, no, it's kind of crazy. It's not like we're standing there with a stopwatch and at 34 hours and 59 seconds, nothing. And then all of a sudden it passes 35 hours and pow, like the whole wall is just magically dry. It's probably not going to happen because 35 is an average. And it means sometimes the paint will take a little more to dry, sometimes a few hours less to dry. So there's this element of give and take in there. How much give and take is there? The answer is exactly 18.7 hours of give and take. So what we know is if we paint a room, you paint a wall with this paint, you're going to see that paint dry within 18.7 hours of the average. Let's take it a step further. If you're in the company and you're in charge of quality control, would you want the standard deviation really high or really low for a can of paint that you're manufacturing? Like the standard deviation of the hours of dry time, would you want that very high or very low? The answer to that is you would want it very low because it means that you're much more likely to have the product match its specifications when somebody is using it. If the standard deviation is really high, that means somebody's going to use the paint and their dry times are all over the place. So just remember, if you're doing quality control, you usually want the standard deviation to be very small because it means the product specifications will be very close to matching what happens in the actual usage. Okay. So let's go back to something that we kind of touched on a little bit, but not necessarily all the way. When we were talking about standard deviation, we mentioned that you have to subtract 1 each time. But why did you have to keep on doing that? Why did you have to subtract 1? Well, to start with, we know the standard deviation comes from the variance. And you have to get the variance first to calculate the standard deviation. These are our 2 different formulas for doing that. And both of the times they have n minus 1. Now, the answer to why you have to subtract n minus 1 is pretty important. We're going to be doing these formulas a lot in the class, so it's going to be helpful to know what's going on here. The answer is you're subtracting n minus 1. It has to do with where you start when you're doing your calculation. And there's exactly 2 places that you can start in statistics. You can start calculating it off of your whole entire population, and that's great if you have enough time and resources to go through and measure data on every single population member. But if you don't, the second place that you calculate it from is off of a sample. Like you go to the population, you take a sample out of that population, then you calculate something based on your sample. Like calculate the variance based on your sample, and then we would generalize about the sample to guess what's happening in the population, because we can't really go and sample the whole, we can't go and measure data on everybody in the population. Now, here's what happens. When you measure the variance of a sample, it's always going to come out less than if you had calculated the variance straight from the population. And we have to put in a fudge factor into the formulas to fix that, because that's really bad news. The fudge factor is the n-1. And we're going to see exactly how and why that works as a fudge factor in just a couple minutes. First, let's take a look at what the formulas look like for population variance and population standard deviation. The ones we were using were for samples. Now, when we go ahead and we're looking at a population, we'll notice inside of there, in our formula, that we don't have an X bar any longer because we're going over to population symbols. So we're going to have a mu. On the denominator, we don't have that fudge factor anymore. We just have plain old capital N for the total number of observations in the population. And we have shorthand for shorthand for the population variance. We're going to refer to that as sigma squared. And the symbol is like a whistle with a square on it. When we talk about population standard deviation, there's also an abbreviation. Instead of sigma squared, we call it sigma, and that kind of makes sense because after all, we just took the square root of sigma squared, so we probably want to call it sigma. So what we're going to do is we're going to take a look at graphically why it is that the sample variance is coming out smaller than the population variance, and that'll get us everything else that we need to know. So let's go ahead and let's take a look at these two sketches, top and bottom. The sketch on the top is the population of wages that's earned by part-timers in some region of the country. And it looks like the wages are going from a low of $8 an hour all the way up to $500 an hour. So $8 an hour is probably somebody that's maybe working a minimum wage job or something like that. And then the people up at $400, $500 an hour, they might be, for example, like a lawyer that's working part-time and they're billing out at $400, $500 an hour. And it looks like our variation is going from 8 to 500. Now, when we go ahead and we look at the sample, notice how the variability of the sample is much more narrow. And it has to be because we only have a few people in the sample. We've got 1, 2, 3, 4, 6 people in the sample. So by definition, our range is going to be a lot tighter. That means that the variability must be less in the sample because the dispersion is much less than in the population. So that's why the sample variance is always going to come out less than the population variance. And that's why when we get to our formula, we have to keep on using that inflation factor right there, that n-1 piece. Okay, so now that we know a lot more about population and sample variances, there's some really cool formulas that you can do once you know how to handle variance. And the first one that we generally end up with is the Chebyshev theorem. So let's talk a little bit about the Chebyshev theorem. The good news about the Chebyshev theorem is that it works on virtually any data set. Doesn't matter if it's bell-shaped, not bell-shaped, like skewed left, skewed right. It's always going to work. So what do you need to make it work? You need two ingredients. You have to know the average and the standard deviation of a data set, and then you can use it. So what the Chebyshev theorem is looking like is it says, if you take your average, your sample average, and you add and subtract 2 standard deviations to it, like you take X bar and you go 2 standard deviations above it and you go 2 standard deviations below it, you're going to capture at least 75% of the data in your data set. So then what happens if you do this 3 standard deviations? What would happen then? If we take our sample average, we add and subtract 3 standard deviations from it, now you're going to get at least 89% of the data in your data set. In the book, they're probably going to do 88.89%, but we can round to 89 just to make our lives a little easier. So if that's the case, how did Chebyshev figure that out? Like, what makes this theorem work? And the answer is, the guy that invented it came up with this proportion. And he said, if we let k equal to the number of standard deviations that we travel from the mean, and we put it in this proportion, 1 minus 1 over k squared, once you plug k in, you're going to end up getting a number like a decimal. You can interpret that as a percentage. Like if you ended up with k giving you, say, 2 standard deviations above and below the mean, you could solve for k And that's going to give you a value of 0.75, which would translate into 75%. So now that we have that, what we can do is we can say, well, how do I actually find that amount of range? It's going to be at least 75% of your data, because we plug in 2 for K, and the percentage we get back is going to be the percentage of data that we'll capture back by traveling above and below that amount of standard deviations. So that's how we found out that at least 75% of our data was within at least 2 standard deviations of the mean. Or rather, within 2 standard deviations of the mean, you're going to get at least 75% of your data. When we wanted to figure out how do you find that 75%, that's where we ended up with part 2 of our theorem. Like, between which 2 numbers do you actually get that minimum percentage? What we can do is we can take our sample average and we can add K standard deviations to it, which is 2 standard deviations, and then subtract 2 standard deviations from it. Okay, so now what we're going to do is we're actually going to go through and do a real live example of the Chebyshev theorem, so we can see what it would be like if we had to use his proportion and crank out an interval estimate. Okay, in this video segment, what we're going to do is a real live exercise of the Chebyshev theorem. And pause the video for a couple minutes, read through the question if you need to. Okay, so it looks like they're asking us to figure out between which 2 numbers are we going to get at least 75% of the time the calories in a bagel. And to start this off, what I'm going to do is I'm going to just take the information that they gave me. I'm going to list it on the left side of my page here. So I have the number 240, and let's do this in black or blue. 240, and then they gave me a 38, and the percentage they mentioned was 75%. And now what I have to do is I'm going to go back and I have to put symbols up to those numbers so I know what they go to. And they mentioned 240 in the context of an average right here. So I have 2 different things that I could use for an average. I have an X bar and I have a mu. X bar, sample average, mu, population average. So how do I figure out which one to use? The answer is, if they don't specify, I'm going to go ahead and assume that I'm using sample data. So I'm going to pick X bar to be that 240. I'm going to come in and say 240 X bar. Now the 38 they mentioned in the context of standard deviation. So again, standard deviation, I have 2 different possibilities. S, sample standard deviation, sigma, population standard deviation. And since we decided that we're using sample symbols, I'm going to call 38 my S value. Now 75% is just a percent, so I'm going to leave it there for now. And the only thing that I can really work with is I've got the components of the Chebyshev theorem. So I'm going to write here 1 minus 1 over K squared is equal to some minimum percent. And my minimum number on that range is going to be like this, X bar minus K S. My maximum is going to be X bar plus KS. Okay, and I'm going to go ahead and put a little answer box next to these because pretty soon we're going to have the answers. And again, what's happening is when I move a certain amount of standard deviations away from the average, I move K standard deviations away, I'm going to end up with some minimum percent of data. Now, between what 2 numbers am I going to get that minimum percent of data? Well, that's going to be in between this minimum and that maximum. Okay, so how do we back all this up to get our answer? The answer that I need is obviously the minimum and the maximum. So I need to know these 2 parts right here. And if I look in the formulas, both of these ends, I've got most of the things that I need to work the formula. I have a X bar already. I have a standard deviation. Here's my X bar, here's my S. What I don't have is my K value. So the K value here is what's going to slow me down. How do I get the K value? The K value is going to come from this part of my equation, and I get that by taking 75% and plugging it into that percentage. So working backwards, I have to take my 75% and I have to set it equal to this equation. I'm going to end up using that information to solve for my k value, and then once I get my k value, I'm going to basically put it into my formulas, and I'm going to use the k value to solve for my minimum and my maximum. So if that was a lot, you're right, it was. Let's take it step by step. Let's clean this up a little bit. And the first thing I'm going to do is I'm going to start to fill out my proportion right here. So I'm going to come along and say, I'm going to have 1 minus 1 over k squared. Now the first change that I'm going to make, so the math is really easy, I'm going to take this inequality right here, and I'm going to switch it to an equality sign, because it's going to be a lot easier to do algebra if I have an equality. And then at the end, when I do my summary statement to the question, I'll remember to switch, I'll remember to put in verbiage for minimum percentage. Now, the second change that I'm going to make is 75% is written obviously as a percentage. I'm going to take it, I'm going to change it to a fraction. What a lot of people do, a lot of students will try to set this whole thing equal to 75 or to 0.75, and it completely makes the algebra a lot harder than it needs to be. So my best friend is I make it as a fraction. Now what I'm going to do here is I need to solve this whole thing for k. And the first piece that's kind of big and ugly in my way is this 1. I need to get rid of the 1 because I have to start to isolate my k term. So how do I do that? Well, what I'm going to have to do is I'm going to have to subtract 1 from both sides of the equation. So I'm going to rewrite the whole equation over again. 1, that's in red. 1 minus 1 over k squared equals 3/4. And now I'm going to make a change to it. On the left side of the equation, I'm going to do a -1 plus 1. When I do to the left side of the equation, I must do the right side. So on the right side, I'm going to come over here and I'm going to do a +1. Or I'm sorry, it's supposed to be a -1. So I'm going to do a -1. And now I'm going to clean this up on the next line. -1 plus 1, that's all going to cancel off right there. That's going to leave me nothing. So I'm going to end up with -1 over k squared equals, on the right side, 3/4 minus 1 will be a -1/4. Okay, now this is looking better. I'm isolating k, but I don't want to go around solving for negative k. I want positive k. So I have to do something to get rid of the negatives on both sides. And I'm going to make a little more space on the screen too. Let's get rid of this part here. And we're going to move this up. Okay, so how I'm going to do this is I'm going to write the whole thing over again. -1 over k squared equals -1/4. And I'm going to take both sides of my equation. I'm going to multiply both sides by a -1. So left side is just like this, -1. Right side is going to be just like that, -1. And what that's going to clean up to be is 1 over k squared equals 1/4. So now how do I knock the 4 out of here, knock the k out of here? A little trick I can use is I can cross multiply. Just like this. And that's going to leave me with k squared equals 4. And k is going to be then equal to plus or minus, well, not plus or minus, we'll just say -2 and +2. And if I'm doing Chebyshev, I only want the positive value. I'm not going to worry about the negative. So I'm going to take the 2, and the next thing that I'm going to do with it is I'm going to bring it all the way up to here. And I'm going to plug it in for my k value right here. I'm going to plug it in for my k value right over there. And let's see how this thing solves out. So take a couple of minutes, pause the video, solve out the minimum and the maximum. Let's see what you get. Okay. So I'm going to do this over here on my right side. I've got x bar minus ks. My x bar 240 minus my k is 2. And my s was a 38. And let's see what happens when I calculate that thing out. I get 164. Okay. For the formula down here on the bottom, the only difference is going to be I have a plus sign instead of a minus sign. So I'm going to fill in virtually the same numbers except for the sign change. 240 plus 2 times 38. And let's see what I get. 316. I'm going to fill that straight in here. Okay, so what can I say that I know now? At least 75% of bagels out there on the market are going to be in between 164 and 316 calories. Okay, in this next video segment, what we're going to do is we're going to take a Chebyshev question, we're going to solve it through once again. And take a minute to pause the video, read through if you need. This is coming from page 140, number 39. Okay, so it looks like in here we're trying to figure out what's the minimum percentage of trials, or the minimum percent of times that a mice will be able to get through a maze in between 4 and 20 trials. So to solve it out, I'm going to start off the same way I did the last time. I'm going to write all the numbers they gave me down on the side of the page. I have the number 12, the number 3, and then 4 and 20. I'm going to start to get these labeled. The number 12 they gave me as, it looks like the average number of trials was equal to 12. So just like I did in the last video, I've got two choices, an X bar and a mu. X bar sample average, mu population average. They also do not specify in this question if my data is from a sample or a population. So I'm going to go ahead, I'm going to use sample data. That means my 12 is going to be my X bar. So I'm going to write that in now. 12 is my X bar. The 3 they gave me along with the standard deviation. So from the last video, the symbol for our sample standard deviation is going to be S. And the 4 and the 20 came up in context of a range of 4 to 20 trials. So my 4 must be my minimum, and my 20 would have to be my maximum. And now to solve this the rest of the way, I'm going to have to start to write out my Chebyshev theorem. I have 1 minus 1 over k squared is less than or equal to some percentage, just like so. And on the right, I'm going to put in the other pieces of my theorem. My minimum equals X bar minus KS, and my maximum equals X bar plus KS. Okay, now if I were to do the same approach I did the last video, and I try to start off with this proportion right here, can't do it. And the reason why is because inside the question, they didn't give me any minimum percentage. So I can't turn around and set this equal to some number to solve out for k. There's just nothing there to work with. So what that means is I have to go to the far right side here first, do a little magic there, and then once I'm able to algebraically set the minimum and the maximum equal to a number, solve that equation for k, I can plug it into my proportion on the left side. So how do I do all this? If I look on the right side, I've got minimum and maximum. I have to pick one of those two to solve for k. And it doesn't matter which one I'm going to pick, I'll get the same answer. Personally, I like to use positives. So I'm going to go ahead, I'm going to work with the maximum. And I'm going to move the maximum a little bit further up on the screen to work with here. And we'll take out the minimum altogether. And first thing I'm going to do to make life a little bit easier, before I plug numbers in straight away, I noticed that if I need to solve out for k, there's going to be some isolations that have to happen. So what I'm going to do is I'm going to take the equation as it is itself. I'm actually going to isolate it for k. And then once I have my own equation for k, then I'll start plugging numbers in here. So it looks like the first thing I would have to do is subtract away my x bar. So I can say my maximum minus my x bar is going to be equal to k times s. And as it looks a little bit nicer, let's move this up. Looks a little bit easier to work with, but I still have my k attached to an s. So how do I clear out the s? I'm going to have to divide both sides by s. And I'm going to go ahead and let me rewrite the whole thing over here. Maximum minus x bar equals ks. So I'm going to divide the right side by s. And what I do to one side, I must do to the other. So I'm going to divide the other side by s. My s's will cancel, and what that now tells me is my maximum number of the data set minus my x bar, my sample average, divided by s, must give me my value for k. So what I want you guys to do is take a second, plug in your values, solve out for k, and let's see what you get. Okay, so when I solve this out, I'm getting k is equal to 2.67, and I'm rounding to the 10th digit. So now what I do is I'm going to take my k value, let's say equals 2.7, which is going to be equal to our k value. I have to take that and I have to plug it into this proportion all the way up here. Say k equals 2.67 is going to get fed in right here now. Okay, let's start to make that magic happen. I've got 1 minus 1 over 2.67 squared. And to make things easy, I'm just going to switch the inequality to an equal sign exactly like I did in the last video, and then just leave it hanging equals what. And what we'll do is I'm going to do 2.67 squared on my calculator. I get 7.12. I'm going to do that again, make sure it's correct. 7.1289. So I'm going to round it to the 10th digit, 7.13. I'm going to write in 1 minus 1 over 7.13 equals. So now I'm going to go 1 divided by 7.13, and I get 0.14. So that whole thing is equal to oops. This whole entire thing is going to be 1 minus 0.14, and then what's that going to be equal to? 1 minus 0.14 is going to give me a 0.86. Okay, let's box this up here. And I can say that what I know now, I'm going to take that 0.86, I'm going to interpret it as a percentage, and I'm going to say at least 86% of the time, the mouse is going to be able to make it through the maze between 4 and 20 trials. So in other words, at least 86% of the time, that mouse will need between 4 and 20 trials to make it through the maze. Okay, so now that we've had plenty of Chebyshev, we're going to go ahead into something called the empirical rule. And we're going to switch back over to our PowerPoint view here. Okay, so what's the empirical rule all about? The empirical rule is really similar to Chebyshev. Just like the Chebyshev theorem, the empirical rule has to do with estimating percentages of data that fall in certain ranges around your average. And when we did Chebyshev, the cool thing about it was it works for almost any kind of data set. Doesn't matter if you're skewed left, if you're skewed right, if you're bell-shaped, if you're not bell-shaped. The part that's not nice about it is it's kind of rough. You have to keep saying at least, you have to keep using a minimum percentage. And that's because we don't know very much about the data. Like we know nothing about the data set, so we can't get very approximate. As we know more about the data though, we're going to be able to make our range estimates a great deal more specific. Now, in particular, if we know that the data is bell-shaped, we can use something special called the empirical rule. So what's empirical rule say? Part one. First thing empirical rule says, if we go one standard deviation above and below the mean, we're going to get more than the majority of our data. I mean, we're going to get the majority of our data. It's going to come in at 68% of your data within one standard deviation above, one standard deviation below the mean. So what happens then if you double up on the standard deviations? If you go 2 standard deviations above and below, well, now you get pretty much almost everybody. You're at 95%. At 95% is almost a full house. So then what happens if you go triple? You go 3 standard deviations. Would that give you 100%? No. Reason why is because we're statisticians. We're never going to give anybody 100% accuracy. But what we'll do is we'll say 99%. So 99% of our data is going to be within 3 standard deviations of the mean. So how do we use this? Let's do an example of the empirical rule. And we're going to say we have our first examination. The average score on that exam is a 74. The standard deviation is a 4. And what I want you to do is find for me the 3 different ranges where we're going to see 68%, 95%, and 99% of the scores. So in other words, between what 2 scores are we going to find 68% of all our test takers, 95% of all our test takers, and 99% of all our test takers? If you need to, pause the video for just a minute to compute it out. Okay, so how does this turn out? Well, first thing that we know is if we want the 68% range, that's going to be what we find when we go 1 standard deviation above and 1 standard deviation below the mean. So 1 standard deviation is a 4. If we take 74 plus a 4, it's going to give us a high side of 78. If we go 74 minus a 4, it's going to drop us down to a 70. So we know that if you took that test, there's a 68% chance you scored within a 70 and a 78. So how about the next one? 95%. If we're looking at 95%, now we have to go double the standard deviations again. So we're going to take 74. We're going to add 2 standard deviations to it. Each standard deviation is a distance of 4. So we're going to add a total of 8 onto the 74. 74 plus 8 will give us 82. The low end will be 66. So just about everybody that took that test, 95% of the students that took it scored between a 66 and an 82. So then where was everybody? Like 99%. 99% is going to connect to 3 standard deviations, and that's going to be between 62 and 86. So if you took that test, there's a 99% chance that you scored between a 62 and an 86 on the examination. Part 2 of the empirical rule. What part 2 says is, let's go ahead and let's think back to where you were when you were at 95% of your data. We had to go 2 standard deviations above and below the mean. And we stop and we kind of think for a minute, and we say, if we have 95% of the data in the data set, that's almost everybody. So if you found somebody outside of that range, like they'd have to be pretty rare. So what do we call people that are pretty rare? The answer is, we're going to call them unusual. So any observation 2 or more standard deviations away from the mean, we're going to consider unusual. So what if you went 3 standard deviations above and below the mean? Then what would you call those people? Like really, really unusual people? Or what would you say? The answer is, they would then be called outliers. So if you go 3 or more standard deviations away from the mean, and remember, this is only working for bell-shaped data. You go 3 or more standard deviations away from the mean, you're finding data values, they're going to be considered outliers. So let's put it to work. We have Jane. Jane comes in. Jane takes our test, and she scores an 88. We need to know, would Jane be an outlier? And what do we have to figure this out? Well, we only know a few things. We know the scores. We're going to assume that the scores on the first test are bell-shaped. Average turns out to be 74. Standard deviation is a 4, and the score is an 88. So if we're going to go ahead and put together what we know, we found out that if you're an observation 3 standard deviations away from the mean, we consider you an outlier. So 99% equates with 3 standard deviations, and when we were researching, we found out that if you score between 62 and 86 on that test, that's going to put you in the 99% range. So all we have to do to classify Jane as an outlier is we have to show that she's exceeding the score of 86. Now, does she exceed 86? Well, she has an 88, so yes, she is considered to be an outlier. Okay, a step further now. We're going to go to the next level. Exactly how many standard deviations is she from that mean? Let's see if we could figure it out. So what we're going to do is we're going to take her score of an 88. And I need to move something out of my window here. We're going to take her score of an 88. We know the average was a 74. So we're going to take the difference between those two. And we're going to get that difference in terms of standard deviations. And we can do that by dividing by 4, which was our standard deviation. It's going to come out to be 3.5. That means that she scored exactly, well, her score was exactly 3.5 standard deviations away from the mean. Now, let's generalize this. We're going to make a formula out of it. We could have done any student score in this formula, so we're going to call the 88 an x value. The 74 is our x bar, and we divided by 4, which was our s. And let's trace all the numbers back into place here. When we do that, the formula that we end up with is called a z formula. And you have to get used to z's because we're going to use z's like for everything we do between now and the rest of the semester, everything under the sun practically. Whenever you see a z, that means standardization. It means somebody standardized something. Now, don't ask why they didn't label that as s, probably because they already use that for the standard deviation. They call it z instead. So if you see standardization, all it means is you're finding the distance between some x value and the mean in terms of standard deviations. And the distance is a really big factor here. You're going to hear me talk about that a lot. The reason is in statistics, we measure our distances in terms of standard deviations. Like if you think of running a race, you might know somebody that runs a race. You might run a race, and they'll say like 5K, 10K race. So the distance in a race is in kilometers. We measure our money in dollars. If we're in statistics, our units are in standard deviations. So that's what our z formula is going to do for us. And when we use the z formula, now what we have is we've got this labeling machine. We can go to any x value, and as long as we know that our average was whatever number it was, and our standard deviation was whatever number it was, and we're bell-shaped, we can start labeling data values as usual, not unusual, outlier. So we have those 3 different categories. We have outlier, we have unusual, and then we have usual. And now the z standardization is going to let us go and label all those different data values. Okay, now the only issue with all of this stuff is every time we're using this z formula, we keep talking about bell-shaped data. So how do you track down an outlier if you don't have bell-shaped data? Can you still use this z-score? No, you can't do that. Here's what you do. We're going to have to bump over to the next slide. And if we need to find outliers in data when we don't know anything about it, like we don't know if it's bell-shaped, we have to go through percentiles. And from percentiles, we have to get into something called quartiles. From quartiles, we're going to get into something called the interquartile range. And then that's going to lead us to how to find outliers when we have data that is not bell-shaped. So how does this stuff all work? Let's start to talk about percentiles first. Now, when we talk about percentiles, some of you might have seen context of a percentile, or you've heard of it before. Like you've taken a test maybe, and you took your test, and instead of getting like a score back, 84%, maybe it was a PSAT, they gave it to you as a percentile. So we're going to find out a lot more about what percentiles mean. And to get there, let's use an example. We have Homer Simpson. Homer Simpson comes in and he takes our examination. And Homer Simpson gets a 88% on his score. Okay, so with an 88%, he's feeling pretty strong. Goes home to celebrate, and then the next day he comes in, and Homer finds out that everybody else who took the test got a 93% or higher. And all of a sudden he's sitting there saying, wow, I didn't do so well compared to everybody else, as it turns out. So what happens is if we just take Homer's score and we compare it to the average, we're not going to get that extra bit of information that we just found out. And that's where a percentile can jump in to help us out, because a percentile is going to give us extra information about what we call relative positioning. And relative positioning refers to how you scored compared to everybody else that took that test. So if you've taken a test, like maybe a PSAT or an SAT, and you get your score back, it's going to be a percentile. Usually that's how standardized tests work. So if you ended up with 85th percentile, it means that you did better than 85% of the people that took the test with you. Now, most of the time when we do context of percentiles, we're going to be working with tests, and a higher percentile then means you did better because you outperformed more people. So is a high percentile always great, or could there be times when a high percentile isn't that good? Absolutely. The answer is yes. Think about going into the doctor, and you go for a physical examination. The doctor weighs you, and then they have a chart that tells them, based on your age and your height, how much you should weigh. Imagine if you hit in the 95th percentile for body weight. Would the doctor come and give you a big award and say, congratulations, you're in the 95th percentile? No, they're not going to do that. They're probably going to send you to the hospital or something like that, because it means that you weigh more than 95% of the other people who also are your same age and height. So moral of the story is we just have to be careful about what context the percentile is mentioned in, so we know, is a high percentile a good thing or a bad thing? Okay, so how do you actually calculate the percentile then? Let's say that we have these scores up on the screen, and these are all from the first test. We're interested in figuring out what percentile the score of 88 is. And what we know right now is that the percentile tells us the percentage of people that we did better than. So some things that we're probably going to need to get this done, we're probably going to need to know the number of scores below our 98, and we're going to call it 98x. We want to know how many scores are there altogether, like the total number of values. So if we take the number of values below x and divide it by the total number of values, we're definitely onto it. Intuitively, that looks right. There's just one extra piece that's missing, and it's called the correction factor. That correction factor is we're going to take the numerator and add 0.5 to it. And we're doing that because we have a small data set. So if you have less than 100 data values, that's considered small, and then we need the correction factor. If you had more than 100 observations, you wouldn't need the correction factor. So once we do out the math, if we have the number of values below x plus 0.5, we divide that by the total number of values, that's going to give you a number like 0.75 or 0.85. So how do you take that and turn it into the 75th percentile or the 85th percentile? Like, how do you go from a decimal to a whole number? You have to hit it with a times 100. So what we're going to do is we're going to fill out the numbers for the case of 98, and that lands us in the 72nd percentile. Okay, so now that we know about percentiles, we're going to take that and apply it to understanding quartiles. Percentiles and quartiles very closely related, and that's going to give us the rest of what we need to know to get into the interquartile range, and then how to understand finding outliers when we have just any given data set. Okay, so we have a data set up here, and what number do we recognize that just doesn't belong there? It's probably the 3, right? So here's how we find out if it's really an outlier. First thing we're going to do is we're going to get the median of the data set. And be careful. If we're thinking about median, first consideration is, do we have an even amount of number of values, or do we have an odd number of values? If we have an odd number of values, we're really lucky. Our median would be just the center number. If we have an odd number of values, we would have to take the average of the inner two numbers, or the two middle numbers. In this case, we have an even data set. So when we go to find the median, we're going to have to average 18 and 19, and that's going to give us back 18 and a half. Now, the next thing we're going to do, we're going to look at all the numbers above 18.5, and now we need to find the next median. So we're considering all the numbers between 19 and 22, and then we need the median there. 19, 20, 21, 22, that's an even number. So again, we have to average the middle two values, 20 and 21. It's going to give us back a median of 20.5. Okay, now we're going to go off the other end. We just examined all the numbers above 18 and a half. Now we're going to examine all the numbers less than 18 and a half. So we need to consider of 3, 16, 17, and 18, what's the third median? And we're going to have to take 16 and 17 because the 3, 16, 17, and 18, that's 4 values. That's an even number. We have to average the middle two numbers, and that's going to give us back a 16.5. So that's going to be our third median. Now, as it turns out, these three medians have very special names. Median 3 is going to be called quartile 1. Median 1, quartile 2. Median 3, quartile 3. And they're synonymous with very specific percentiles. Quartile 2 with the 50th percentile, quartile 1, 25th percentile, and quartile 3, 75th percentile. So what we just found out was a really fast way to get the three main percentiles, the 25th, the 50th, and the 75th. Okay, now what we're going to do is we're going to take quartile 3 and we're going to subtract from it quartile 1. So we're getting the distance across the middle 50% of our data set, and that's going to be 4. 4, we have a really special name for that 4. When we subtract Q3 minus Q1, whatever number we get equals what we call our interquartile range, which we're going to abbreviate as IQR. That's what's highlighted in blue. Okay, with the IQR, let's put our quartiles back here. With our IQR, now we have everything we need to start scanning for outliers. We're going to go to quartile 3, and we're going to add 1.5 times the IQR. And it's always going to be 1.5 times the IQR. The 1.5 is a number that we use by convention. That gives us 20.5 plus 1.5 times 4. 26.5 is our result. Now, we're going to go into the data set. We're going to check and see, do we have any numbers above 26.5? If we do, those are considered outliers. For us, we don't have anything up there, so we're cleared for outliers on the high side. But where else can outliers be? And the answer is on the low side. So now we have to scan the low side of the data set. How do we do that? Quartile 1 minus 1.5 times the IQR. And that's going to give us 16.5 minus 1.5 times 4. The answer to that is going to be 10.5. So we're going to go into the data set. We need to see, is there anything up there less than 10.5? And right away, that's going to be a 3. And 3 is going to be our outlier. Okay, so if 3 is our outlier, what do we do with the 3? Should we leave it in the data set? Like it's part of the data set, it has to stay in there because it's a legitimate number. Do we pull it out of the data set? You know, it's an outlier, it shouldn't be there, it's messing things up. Which one? And the answer is neither. What we want to do as statisticians is, if we discovered an outlier, we're going to investigate. We need to find out, was that a typo? Did something happen to the machine that was recording the data? Is it alerting us to something much larger that's wrong with the data set? So we want to make sure that we have a chance to look into it and find out what's really going on. Okay. So the next topic that we're going to speak about is standardization. Imagine that we take our first test, MAT 150 test, and somebody's taking our test, they score an 85 on it. 3,000 miles away, UCLA Law, somebody scores 5 on their test. Is it safe to say that 85 is better than the 5? 85 is a much higher number, so can we definitely say 85 wins? No, we can't do it. And why can't we say 85 is the better performing student? Well, do we even know what test the person at UCLA Law was taking? Do we know how many points it was out of? Is it, what kind of professor was it? Was it an essay test, or What were the different parameters of the exam? Was there extra credit on that test? The Mat 150 didn't have extra credit. So there's a lot of parameters that we don't know the answer to. We can't do a direct comparison. So how do you take two different scores from two different data sets and get them on the same sliding scale of comparison? Standardization. Standardization is going to help get us on the same sliding scale. So standardization will work on any data set, and it works on relative positioning, meaning it works on figuring out who has the best performance relative to everybody else who also tested. Now that's similar to percentiles, but much more powerful than percentiles. What do you need to use standardization? The answer is we need just two ingredients. You have to know the mean of the data set and the standard deviation of a data set. And then you'll have everything you need to use to determine standardization. So what we're going to do is we're going to take two examples that are both very different from each other. They're almost like polar opposites, and we're going to practice standardization in both places. And what's going to end up happening is standardization is going to come down to the z-score. So it's something we've used before, just a new application of it. Okay, so in our first example here, what we're going to do is we're going to use example 329 on page 142 in the book to work through, but we're going to do the example a little bit different than how they present it in the book. We're going to approach it from a graphical position because there's something I want to show you visually, and then we'll go ahead, we'll convert it to numbers and a formula. So take a minute to pause the video if you need, read through it. Okay, so it looks like what's happening is we have the student, they take two different tests, a calculus test and a history test. And we have to figure out, based on knowing the average and the standard deviation on both tests and their scores for both tests, which one they actually did better on. So I'm going to start by taking all the numbers that they gave me, and I'm just going to write them down on the screen here. I'm going to put up here calculus, abbreviate for calculus, and I'm going to write down there's a 50, and there's a 10, and score of 65, so I'll put down a 65. I'm going to do the same thing for history. I'm going to write down all the numbers they gave me. We have a 25, and we have a 5, and then we have 30. Okay, so the first thing I need to start doing is I have to figure out what symbols go with these different numbers. And when they started to talk about the 50, they said, or actually the 65 came first. They said the student scored 65 on the calculus test. So I'm going to go ahead, I'm going to print in right away. 65 was my score. And the next number that they gave me was a mean of 50. Right here. Now, as soon as I see mean, I have two symbols that come to mind. One is a sample average, an X bar, and mu, my population average. So how do I figure out which one to use? They didn't specify in the question whether our data is from a sample or a population. So if they didn't specify, we're going to go ahead and assume we're working with samples. So I'm going to assign the X bar to be my 50. Okay, the next thing that they tossed out was the standard deviation was a 10. And again, if I'm dealing with a standard deviation of 10, there's two different symbols I have. It could be S or it could be sigma. S, sample standard deviation, sigma, population standard deviation. And I'm going to go ahead and I'm going to be consistent. I'm going to use the symbol for my samples. So I'm going to assign S to the 10. And I'm going to do the same setup to history. I'm going to go ahead and I'm going to look in, see what happened with the history test. And they told me 30 was the score on the history test. So that means I can write that in. The history test had a mean of 25, so that's going to be my X bar. And the 5 is mentioned as the standard deviation. So the 5 becomes the S. Okay, now what I'm going to do is I'm going to take the information from the calculus test and I'm going to put this on a number line here. In the middle, I'm going to label my average. So here's my 50. That was my X bar. And I'm going to make 2 little marks here. I'm going to go above and below the 50 by a distance of 1 standard deviation on each side. A standard deviation is 10, so that means I'm going to go up to 60, and I'm going to go down to 10. Now I have a range of 1 standard deviation around the mean. Now I'm also going to go ahead and I'm going to mark their score on here. Their score was a 65. So I'm going to pencil in their score right there. I'm going to do the same setup for the history. I'm going to make a number line right here. In the center, I'm going to drop in the average, which was 25. And I'm also going to make the same range. 1 standard deviation above 25, 1 standard deviation is a 5, so it's going to put me 30 at the high side. And on the low side, it's going to be a 20. They scored 30. I'm going to pencil that in right here. I'm going to write, this was their score, have that in magenta. Okay, I'm going to go up back to the calculus number line that I started with. I'm going to start at the 50, and I'm going to walk about right up there to the 60. How many standard deviations did I just travel? It was 1. So I'm going to write in a little note that says I traveled 1 standard deviation. And now I'm going to walk the rest of the way to the 65. And that's half a standard deviation more. So I'm going to go ahead and write in 0.5 S. I'm going to summarize all of this. I traveled altogether 1.5 standard deviations. Now I'm going to do the same thing for history. I'm going to start at the 25, which is the average. I'm going to walk up to 30, and then I'm just stopping for good because 30 was my score. I traveled 1 standard deviation to get there. So I'm going to mark that here and summarize it right there. Okay. So now I'm going to compare the 1, and I'm going to compare the 1.5. Which one is highest? It's the 1.5. That's my winner. It means that the student actually scored better on the calculus test. Now, how do we know that? What made that work? Let's go back for just a second. If we're looking at the calculus situation, we take a look at all the people that scored within 1 range of the average. And want to know, did our student beat all those people? Absolutely they did. They're all the way out here. So they pulled very far ahead of that pack of all those who scored within 1 standard deviation of the mean. Now, did they do the same job in history? Did they do that well also? Well, down in history, if we circle everybody that scored within 1 standard deviation of the mean, well, their score was just on the leading edge of that. So no, they didn't pull as far ahead from the pack as they did with the calculus test. And that's exactly why the relative positioning was better when they took the calculus exam. Okay, so if we're on the exam, do we have to draw out all these diagrams, or is there a way to quantify this more quickly? Yes, there is. We can quantify it quickly. So how do you do this? By formula. To get this 1.5 up here, here's what really happened. We actually took the score of the 65, and we took the difference between the score of 65 and the mean. We get the difference between those 2 numbers, and remember, whenever we're looking at differences synonymous with a distance, in statistics, what's the unit of our distance? The answer is standard deviations. So what are we probably going to divide by here? The answer is 10, our standard deviation. So in terms of symbols, what we have here, our 65, we're going to call that X because we could have done this for any given score. It didn't have to be 65. Our 50 is going to be our X bar, and our standard deviation is S. So what we just really did was we used our Z formula, and we did our standardization application. Now, we can do exactly the same thing for the history situation. So I'm going to move this up here, and let's go to history. For history, if we set up for this as we're going to use 30, take the distance, the difference between 30 and 25, And we're going to take that total distance. We want it in terms of standard deviations. So we're going to divide by our standard deviation of 5. That's going to bring us straight back to 1. And it's using the exact same formula. Okay, so what we're going to do now is we're going to do one more example of this. And then we'll know virtually everything we need to know about how to use standardization. Okay, so in this case, we're doing another example of standardization, but it's going to come out very different than what we looked at in the last example. This is from page 154, number 15. So take a couple minutes, pause the video if you need to review it. Okay, so what they've given us is we have 3 different scenarios, A, B, and C, 3 different test scores, and on each test, we have an average and a standard deviation. So we need to figure out what's the best relative position using standardization for all those 3 scores. And if you need to, pause the video for a minute to work out the calculations. Okay, so I'm going to go ahead. I'm going to put what I have up here on the screen. And we're probably noticing that this one came out really different. All of a sudden, we have all negatives for the standardization. How did that happen? And the reason why is if we look at the x value for each of these, every x value is below the average this time. So that's what made our z signs all come out negative. Like if we look over here, all of these numbers have negative signs in front of them. And the reason why I circle that in green is because when you see negatives with z-scores, I want you to think of money. Would you rather owe somebody 93 cents, 85 cents, or $1.40? Now, most of us would rather owe somebody 85 cents. And that's why score for B is actually the winner. What's happening is, if our z-scores come out negative, the best score is going to be the one that's closest to 0. So that's what we have to pick. So let's just go ahead and let's summarize all the different things that we've learned about standardization. If it turns out that we have 2 negative scores, which one is going to be the best? 2 negative scores means that we're going to pick the z-score that's closest to 0. That'll translate into the score that was the highest. If we have 2 positive z-scores, that means that we're going to pick the highest z-score. If we have a positive z-score and a negative z-score, we're going to go ahead and we're going to take the one that's positive. That'll be the highest score. And if we end up with 2 z-scores that are the same, what do we do then? The answer is it's a tie. We can't tell. Both scores are the same relative position. So remember how to evaluate all 3. That's a positive, negative, and when you have even z-scores, or the same ones, that's definitely going to show up on your test. So you need to know how to react to either of the given situations. Or actually, there's 4. Z-scores are all positive. Z-scores are all negative. 1 z-score positive, 1 z-score negative, and when the z-scores are all the same.